So, good morning everyone. My name is Nanda, and I'm going to take a talk on quantum cryptography here. So, how many of you think that quantum computers are a development which will bring out good to humankind? Hands raised, please. How many of you think that quantum computer is useful? Good. So, and how many of you think that quantum computers are threat to humankind and especially to our current cybersecurity systems? Okay, I see one hand, two, three. Okay. So I am here to talk about it. So there is nothing that I can talk because my friend has given an excellent introduction about me. So I will just straightly move on. So before that, before I start, there may be some terms or mathematical terms which you may not understand I use here. Please feel free to ask or just Google it. Next. Okay. So one of the research studies has shown that the security threat members are collecting encrypted data, a vast amount of encrypted data. So you may think, what is the use of collecting those big files which is encrypted and we cannot use it? By the way, the files may be like government secrets, research papers, or it can even contain some financial details. So it cannot be means publicly available, but they are collecting it and storing that. It's encrypted, no one can see it. What is the use? Do anyone think that? It's completely encrypted and no one can decrypt it now. Any use? Right? Everyone thinks that is illogical, right? But what their motive is, they are just storing it now, and once they get a hand on quantum computers, the encryption can be easily broken. I will tell how it works in future slides, but they are collecting it and storing it now so that they can use a quantum computer in the future and extract the data. The previous slide. Okay. So this phenomena or method is known as store now and decrypt later, SNDL, and it is one of the most important threat which quantum computers have put forward into. And addressing that, in response to it, the US Congress has also noted this point and passed a bill about it. And it stated that all the national agencies should shift into quantum resistant cryptographies. So this is one of the NSA's report which states that a sufficiently large quantum computer, if built, would be capable of undermining all widely deployed public key algorithms. So we have seen that we are mostly using RSA algorithms right now, and once we have a capable quantum computer in our hand, it will be easily broken. We can say that even the most secured ones can be broken right now with a quantum computer. Not right now because it's completely under development, but once we have enough qubits of power, we can definitely crack into it. And this is one of a member I don't think you need introduction into. He also stated something that you have to note in this interview.
In a 5 to 10 year time frame, quantum computing will break encryption as we know it today.
So everyone has noted about this, but no one came and have put their thoughts forward about how to fix this, right?
In a 5 to 10 year time frame, quantum computing will break encryption as we know it today.
So before I start into quantum cryptography, I would like to guide you through the evolution of cryptography, right? So everything started before 1970s. So if you want to share anything in before 1970s, next slides. You have to go meet a person in person, and you have to take a key or make up a key, and you can then encrypt this data into means with that key and can be decrypted with using that same key. So everyone has seen that this is a symmetric key algorithm, and the same key is used for both encrypting and decrypting. This method of communication is safe until your key is exposed or leaked somewhere. And you may see that symmetric key algorithms are not always the best one, because once the data means the key is leaked, you cannot do anything. The data can be easily decrypted. So, and it is not always possible to share that key in a secure manner. So you cannot meet someone and share a key in person every time, right? So, and it is not also possible to you to just phone call someone and tell this is my key and use this and this. What if your call is being intercepted, or you just send a mail or something to them which can be intercepted. So seeing all that, next slide. These three members has introduced RSA, which we know today, and most of the means cryptographic algorithms are based on RSA. So these three members are the core responsible ones who created an algorithm which is being alive for 40 years now. So how it works is, if each person will have two large prime numbers, and we will multiply those two prime numbers to get an even larger number, which we make public. So the red ones are private and the green ones are public. If I need to send some message, I will take that big large public number of the receivers, and then I will encrypt it so that I can send the data there. But it can only be decrypted with the two key means prime factors of that big number, and you cannot decrypt it with the public key one. So if you want to decrypt it with public key one, you have to do the factorization of that big number. So here I have taken a large number. You may see it's large, but it is the starting means length of means numbers in RSA. So it's, I think, 313 digits. It's the, I think it's 128-bit one. Next slide, sir. So now we can see that factorization can, if we factorize that big number, we can decrypt that information, right? So let's see how we means generally do factorization of these numbers. So in classical computing, as we know today, just bits, ones and zeros. We have taken, if they say we taken the most powerful machine in the world and we have fed it to means decrypt or factorize that big prime number. The general algorithm used is known as general number field sieve. So it is based on brute force method, and if you want to crack the RSA algorithm, it will take like 16 million years for the starting one, and how you increase that bits, as you increase the bits, the time required will be much more. No, sir, please slightly. So now coming to quantum computers. The quantum computers, as we all know, can do fast computing, and not only that same algorithm we have to use here, because there is an algorithm known as Shor's algorithm, which can compute these factors of large prime numbers in seconds. So using that, you can easily crack RSA. So if I have just have a quantum computer at my home, I can just go and plug in my pen drive with the keys, and I can decrypt anything I want to. So now it is not possible currently, because now we are just developing it, and we are exponentially increasing qubits. So qubits are the number of bits which is being processed right now. Next slide. So now coming into my topic, which is quantum cryptography. So as we have known, RSA will not survive the era of quantum computers. So we definitely need a way to keep our secret forever, right? So that's why where quantum cryptography comes in, and we will specially look into quantum key distribution. So as I told, key distribution plays the most important part here. Once you have securely communicated your keys, everything is fixed and everything works completely fine. So next slide. So in 1984, two people known as Bennett and Buzzard introduced a protocol known as BB84, which may be not popular but one of the popular ones in quantum cryptography. So what they did is, as we all know, RSA is completely based on mathematics, right? They doesn't want mathematics to be involved, because once mathematics is involved, it is breakable, right? So what they did is they changed every concepts of the classical computing and take it into physics one. Next. So let us understand how it works. So we have light, which is the fundamental thing, and the particles are known as photons. And photons is not only just a particle, it's also a wave, so it oscillates. So it may oscillate in different directions, right? And we are going, what the oscillation part, we have to remove some oscillations, which is known as polarized light. It will just filter out all the oscillating part and give us a one oscillating photon in same direction or the same angle. With that, we can send that same polarized light to someone. If the person is holding the polarizer in same angle, they will get this light on the other hand. If they hold it horizontally, and I send the polarized light in vertical manner, it just bounces off and we will not get an light passing through that. So based on this phenomena and few means algorithms to communicate, they built a protocol which is known as BB84. So you may think that completely changing infrastructure, and we have what we have now is completely based on bits and electrical signals, and converting everything into means photonic ones is completely different, and it's very difficult, as we know. These are just simple algorithms which can be implemented. As we all know, it is not feasible. Everyone cannot change the means already implemented systems into especially designed systems for communicating. So this is where post quantum cryptography kicks in. In 2016, I guess, NIST means opened a forum, and they are called for papers for post quantum cryptography. So post quantum cryptography is a method where we use the same infrastructure what we have right now, and use the same infrastructure, but keeping the cryptographics quantum resistant. So we have no need to change every infrastructure right now. It just needs software changes. So they called for papers, and like 86 papers came in, I guess, and after rigorously testing all that papers, 4 papers were shortlisted for the standards. And from that 4 papers, 3 papers were based on lattice-based cryptography, mathematical lattices. Next. So let us see how it works now. So next. So we have 2 vectors here, R1 and R2, and we are going to take all the points that it may traverse like this, and we will make a lattice with that. So it may go in different points with the combination of these 2 vectors, and this is known as the lattice points. Now we take a random point C there. Our means goal is to find the nearest lattice point to the C. So what we can do is go 2 times R2 and 2 times negative of R1 to get that point. It's easy, right? Now just imagine these 2 vectors, B1 and B2. These 2 vectors make the same lattice points, but now it's, I guess, will be difficult to go to that same point there. Let's see. So we will trace with these 2 vectors. And you can see obviously the number of steps required to solve this has increased just by changing the 2 vectors, right? So to solve this, I need 8 times of B2 and 8 times of negative B1 so to solve this. Now You may think it's easy, it's in just two-dimensional. I explained it in two-dimensional because it is easy to understand. What if I take it to three-dimensional? It becomes difficult. And also, if you want to see it in three-dimensional, it's also easy for computers. Even supercomputer can crack this. So then we increased into 100 dimensions. Now the problem is seriously hard right now, and still the quantum computers can crack it. Let's say we have taken 1000 dimensions. What happens then? Because there is no known algorithms to compute vectors in that much dimensions, and it's not as easy as just factorizing large numbers. Next slide. Now let's see how this works to encrypt the data. In the same kind, we will keep R1 and R2 private, and we will share these two vectors, which is the difficult ones, to the public one. So if I take a point there, let's say 7 there, and we will add a little bit distortion so that it doesn't point to the same lattice point, we will add a little bit of noise to it, and then we will use these vectors to compute the exact part, and it is difficult. I have used just two dimensions here. Imagine it in 1000 or 10,000 dimensions. It will be completely difficult. But the receiver can easily go with their private key to trace back to that one. So this is the core part or the core fundamentals where the quantum cryptography lies on, and these 4 papers are shortlisted for implementing for standards. So I have explained it in a simple manner, but when you go through the algorithm, it's completely different, and it's hard to understand for a person who is coming from classical cryptography to quantum cryptography. So I would, for my experience, quantum cryptography and modern cryptography are completely two different things. Just we have to know that we have to work on post quantum cryptography. As we all know, the number of qubits is exponentially increasing, and one day even one of you will get a quantum computer in your house, and he can decrypt all the information which is currently on the internet or around the servers. So this is where my title lies: if quantum bit raise, secrets fall. And next slide. This is where I end my talk. And any doubts? Any questions? Yeah.
Thank you very much. So, question is very simple. See, you know ransomwares.
Yeah.
So, ransomwares basically they locking the files based on cryptography using RSA. Okay?
Yeah.
Basically asymmetry.
Yeah.
So, in order to crack that encrypted file, we need that.
Yeah.
So, using any kind of quantum algorithm or any quantum-based technology, can we able to find?
Yeah. As I told, as it was a good question though. So ransomware encrypt that data using these algorithms means RSA. It's completely based on RSA. What we are working is completely RSA, and RSA can be broken. And as he said, if we have quantum computers, we can also deal with the ransomware stuff. But at current stage we cannot process it because we doesn't have the number of qubits required right now to compute that decrypt that ransomware encrypted files. So yeah, in future maybe we will look into that, but if we come back to the post quantum cryptography, definitely the threat actor will go with this one rather than using the classical RSA one. Any other questions? I hope I answered that, sir.
Yeah, thank you.
Thank you, sir. Any other questions, please? Yeah.
Follow up to the question,
Yeah.
since decryption becomes easier when quantum computer arrives, so will be like new encryption model is also based on quantum computing will appear.
Yeah, it's completely based on quantum computers. Oh, you are guessing that completely shifting into quantum computing.
Yeah, new encryption model based on quantum
computers.
And the attackers also use those encryption models to perform attacks.
Okay. So what he has asked is, what if we have means completely have a encryption model which is based on quantum cryptography. Switching to quantum computers will take time, obviously, and till then it's not like that everyone will get quantum computers instantly, right? So we will be using that quantum computers to communicate. For two quantum computers, we will definitely have algorithms based on quantum computers. But when we talk about communicating now without the secrets falling, we have to use these algorithms. That it's like let's say just keeping our secrets safe right now without relying on quantum computers. Any other doubts?
Is it currently used anywhere?
No, sir, it's currently under development, and the ISO standards is also working on it. But as I have told, US government has passed a bill to transition into quantum resistant cryptography, and these 4 papers are there to maintain the standards, and it's still in research process. Any other questions? Anything? Okay, then I think I can sum it up. So I have attached all the research papers and references to that QR code, and I may update few more research papers there. You can scan it or just keep the link with you, and you can see the details of all the research papers and the, as I told, the NSA's report which came in. So all the references are there and you can check it out. So this important to always look into the future, and quantum computers are currently developing in a very fast pace, and we have, as a security researcher and security members, we also have to keep up the pace with the new technologies. So it was the one I would like to share with you all, and I hope that the time you invested paid off. And this is Nanda signing off. Thank you.